Today we would like to compare the line integrals. First thing is scalar line integral when you have a curve C and a function that is scalar, either f of x and y or f of x and y and z. The notation for this is f, the scalar function f, ds, s for the arc length over the curve C. And how we compute it is, so again, this is the notation. How we compute it looks like this. We plug in f of r of t. What is r of t? R of t is how we parameterize C, and t is between a and b. That means that parameterize x and y in the f, x and y or x and y and z, and go from a to b. Then ds is replaced by the magnitude of r prime of t dt. So this is the arc length element. Now, the next step is, what does this mean? It means if you have a curve in the space, for example, and you look at the height in the xy plane, from the xy plane, you're finding the surface area of that below that curve, or the net surface area if the curve goes under xy plane. The other meaning of this is basically if f is a mass density, or any density for that matter, then the integral is the total mass. So any of these two interpretations will help you understand it better. Again, one other thing that I want to add in here is this is literally f of x of t, y of t, and z of t, when x of t, y of t, and z. Next is the vector line integral. Again, it's over curve C. This time, the function is a vector function, or and what is important here is the direction. So you parameterize C by r of t, and t goes from r of a, and c goes from r of a to r of b. Now, the notation for this is f dot dr. Again, because this is a vector function, you want to have elements that is a vector element over C. Then computation this time is going to be equal to a from a to b, f evaluated at r of t dot r prime of t dt for computation. A lot of times people like to actually know the meaning of this one, and the meaning of this one doesn't appear very well from the computation part. It appears from the definition. The definition of the vector line integral is f dot t that is the tangential, this is the tangential component of f ds. And this is the arc length element. So this tells me more. It means that if there are the vector field f is going like that, every time I compute its tangential element by dotting it by a unit tangent vector t. T is the unit tangent vector, and then computing that component times a small, tiny arc length, and summing it all together. And that's exactly work. So the other type of, again, we did the notation, we did the definition, and we can do computation. What we want to add to this is that there are two ways that f is represented, with f1, f2, and f3, or with p and q and r. So this method is telling us, the computation method tells us that f at r of t dot r prime of t is going to be p of x of t, y of t dot x prime t. So instead of, sometimes this is the other notation that you may see. Instead of f of r of t dot r prime of t, you may see p dx plus q dy plus r dz. A vector line integral over c of f dot dr. You're really computing for a conservative field that is equal to gradient of its potential, you're really computing gradient of f dot dr. And this is the integral from a to b of gradient of f and r of t dot r prime of t dt, which it turns out by chain rule, this is exactly equal to the derivative of f of r of t. Derivative, antiderivative by Calc 1, fundamental theorem of calculus, this is going to end up to be f of r of t from a to b, or f at r at b minus f at r at a. We typically say that r of b is the endpoint, or we call it q, and r of a is the beginning point, and we call that p. So this makes our life a lot easier. Every time you see conservative fields, find potential to this f of q minus f of p makes potential f an antiderivative, analogous to Calc 1 antiderivative of the vector field f, and the computation becomes like that. With conservative fields, you have to either have a very nice domain, or you have to check, that is, either r squared or r cubed, or you have to check if it is simply connected. And you have to check that curl of f is equal to 0 before, so domain, and then you can find the potential. So Green's theorem is another way of computing vector line integral. Green's theorem connects the vector line integral over a closed curve. So the curve has to be simple and closed, like that. When the curve is simple and closed, you can shade the area inside. This integral gives you circulation on the curve, on the closed curve. And you can actually use all the circulations inside, which is the little curls, add them all together. Adding all together on the area is going to be d curl of f dA. So sometimes when the line integral is difficult, you can use the curl and the area. You can use the curl and double integral to compute the line integral. This double integral is the double integral from 15.2 section. Now, why Green's theorem, or how do we use it? Typically in a Calc 3, you may get a verification. Or when the line integral is difficult, you may compute. You may compute the double integral. Or for certain vector fields, such that curl of f is equal to 1, you can use to compute area. And this is when area is difficult to compute. We also talk about regions with holes. Green's theorem holds for regions with holes, and that actually is when you have a hole in here, if the outer curve is counterclockwise and the inner curve is clockwise, then Green's theorem is true in this region. Green's theorem for outer is always counterclockwise. For inner is clockwise. So what you want is, if you curl your hand around the shaded region, you want your fingers to go toward the direction of the curve. And in this case, integral over C1 f of dr plus integral over C2 f of dr is going to be equal to the del integral d of curl f dA. One last thing, sometimes when you see the notation, C is equal to boundary of D. So they start with a region and define C to be the boundary of that.